Welcome back. So we were considering our coffee cup system and whether or not it should be treated as open or closed, or a control mass or a control volume. So recall a control mass is one with a fixed mass or closed system, and a control volume is an open system where mass can cross the system boundary. So I said, well, I want you to consider the coffee in the mug. So the answer is a little bit tricky in that, okay, what do we mean by the coffee in the mug? Are we pouring the coffee into the mug? Then I'd argue that's best treated as an open system. If we're looking at maybe, is there any evaporation of the coffee from the mug? Yeah, again, that would be considered an open system. On the other hand, if we don't think there's going to be any evaporation, and all we're looking at is, let's say, the coffee cooling in the mug, that would be a closed system. So it requires a little bit of thought sometimes. I mean, that's a little bit of a fun example. But some systems, it may be just like that, a little bit tricky. And we'll cover some of those trickier examples as we go through the class. The second system is pretty straightforward. So we want to know, is the microchip in your computer best treated as an open or closed system? Well, if the system is just the CPU, then then it is a closed system. But if we're considering the air around the CPU, then obviously the air has got some movement associated with it. And we'll use this as an example a little later in the class too. But as I think I've mentioned already, the microchips that we use, the microcomputers, the brains that are in our laptops in particular, have to dissipate quite a bit of heat. And that puts an incredible demand on the heat removal from that system, the heat transfer from the system. So we can only generate as much power as the waste heat can be removed from the microchip. So we'll discuss the cooling of a microchip in an example a little later on in this class. Okay, back to our definition. So again, we need the vocabulary before we can actually start the quantitative analysis. So properties are the characteristics of the system. And specifically, we care about the thermodynamic properties. And those describe the state of the system, or the thermal properties of the system. So the state is the condition of the system as described by the thermodynamic variables, so the thermodynamic properties. Steady state means we have a system where those properties are invariant. And that's important for us because in thermodynamics, in order for us to define a state, the properties have to be invariant. Okay, so what types of properties are there? There are extensive properties, and those are properties which depend on the extent or the amount of material that's present in the system. These properties are additive, and the best and easiest example is mass. So if I have so much material in the system, if I have twice as much material, I have twice as much mass. If I have volume is another good example of an extensive property. If I have twice as much mass in the system, I have twice as much volume in the system. Intensive properties do not depend on the amount of material present. These are properties which are not additive, things like pressure or temperature, which are not additive. If I have my brick and then I have another brick at the same temperature, the mass of the system, let's say, is twice as much. Let's say they're two bricks of the same size, but the temperature of the bricks are the same. So temperature is not an additive property. It's an intensive property. Equilibrium, which I've already mentioned a little bit once, is when a system is unchanging in terms of its thermal, mechanical, phase, and chemical characteristics. Some of that gets into a lot of detail that we're not going to cover in this class, but the thermal equilibrium means essentially there are no temperature gradients in the system. Mechanical equilibrium is in terms of the force balance in the system, that the system is equilibrated or balanced in terms of the forces on the system. Phase is with respect to phase change, so solid, liquid, vapor, things like that. Chemical means there's no spontaneous chemical reaction that's occurring in the system. It's chemically equilibrated. There's no change in the composition. And a process is the path that connects between different states, between two states in particular. So a process is the path that's followed to connect one state of the system to another state in the system. So some of these may be a little bit odd right now. Again, I'd encourage you to use your reading material to help support your understanding. But it'll make a lot more sense when we start doing some examples. We can say this is a system, this is the state, this is the path, the process that the system undergoes. So let's move on. Let's start talking about some specific thermodynamic properties. Well, we've already mentioned temperature. We can tell that's going to be very important because we know it drives heat transfer. It's used to define the state, or it is a property that we can use to define the state of a system. But there are some other properties that I expect you're quite familiar with already. Density, which is the mass per unit volume. Specific volume, which is the inverse of the density, so it's volume per unit mass. Pressure, and there's both absolute pressure and relative pressure, and again, good reading material in the references if you want to learn more about the differences between those, and temperature. Those are 4 intensive thermodynamic properties. So let's talk about temperature a little bit more. Now, pressure, we already talked about, all the issues associated with the many different units that there are for pressure. So be aware there are many units, and you're going to have to be able to move between the different units using conversion factors. Temperatures, there are really only 4 units for temperature, and those are on a relative scale and an absolute scale. And in thermodynamics, we only want to use the absolute scale. There are times where you can use the relative scale and you'll be fine. But if you always use the absolute scale, you'll always be using the correct analysis, the correct tools. So I strongly encourage you to always convert into absolute units. And in British and SI, there are 2 different absolute scales. And there's a conversion factor we'll go through right now between the 2 scales. So the SI relative scale, the SI units are Celsius. The absolute scale are units of Kelvin. And we can convert between the 2 just using this expression. Okay. So we just take the temperature in Celsius units, add 273.15, and that's going to give us units of Kelvin. So this, again, is the conversion from the relative scale to the absolute scale for the SI system. And if we're looking at the British system, we know the relative scale is degrees Fahrenheit, and the absolute scale are degrees Rankine. And we don't often use the British units. We're trying to standardize towards SI units around the world. So I'd strongly encourage you to convert everything into the SI standard. And the conversion between Fahrenheit and Kelvin is just a multiplication factor of 1.8. Okay. So these are just a few of the properties that we're going to use in this class. These are all intensive properties. In other words, each one of these properties is independent of the amount of mass present in the system. We'll build additional thermodynamic properties into our skill set as we move along, but let's start with these for right now. Okay, so I know you're familiar with these properties and you've seen them before. So temperature and pressure we already discussed, and we've talked all about their units. So what I want you to do in this question to answer more specifically are what are the units of density and what are the units of specific volume? And I want you to consider those units, and then in the second question here, I want you to identify, are these properties intensive or extensive? I've already told you. But I want you to consider why the pressure and the specific volume are intensive properties. And we'll cover that next time. Thank you.